Well, we're going to explore in our series, The Boundaries of Reality, we're going to explore what I like to call beyond coincidence. And this is part one. And we're going to explore a little bit a number of things, one of which is what I call our epistemological challenge. Epistemology is a fancy word for simply the study of knowledge, its origin, its scope, and its limits. If you take that in college, you're wasting your time because it's usually part of the philosophy department, and all they do is massage different definitions of words without dealing at all with tools of how to deal with the understanding what's really true as we try to explore our reality. And so I want to start, when I do this kind of a talk, I usually walk in wearing these beads. But I usually do it just to freak out the sponsors. They wonder, what have they done here? But I want to talk about these beads before we start, because I want to give you an IQ test. Now, the way this all came about is I have a little craft workshop where I do models and things, and I spilled on the floor a whole jar of these black and white beads. So as I picked them up, I decided I didn't want that to happen again, so I just picked them up at random and put them on this thread, and so that they now have integrity. I could take a few off that I need or whatever. Except after I picked them up off the floor, I was startled to notice something. Because as I looked at it, anybody here radio hams that know Morse code? Hey, there we go. Okay. Well, I noticed there's did it, and then da dit. Did it is I, and da dit is N. It's the word in. Then there was a dash, which is by itself, that's a T. And then there's 4 dots, that's an H. And then there's a single dot, E. In the. Then there's a B, E, and a G, I, in the beginning. And to get right through it, I was stunned to discover that in Morse code, we have in the beginning, God created the heaven and the earth in Morse code. And that all happened by random accident. I picked these off the floor randomly and put them on that thread, and they just came out that way by accident. How many believe me? How many are accusing me of being a liar? The liars have it. You obviously, if I try to tell you that happened by accident, you know I'm pulling your leg. You know that I'm kidding. If I had better delivery, I could make the whole thing humorous, but you get the idea. Okay. So the probability that this happened by accident is, as far as you're concerned, absurd. It's not a 50-50 chance. It's something far greater than that, right? Well, did this happen by chance or by design? I want you to ponder that for a moment. There are 347 beads on this string. Now, there's only 2 types of beads, a black and a white. So I have an alphabet of 2. I have 347 of them, right? So the probability of getting any specific sequence is 1 chance in 2 raised to the 347th power. Or putting it another way, it's 2.8669 times 10 with 104 zeros after it. That is a very big number. In other words, that is really unlikely. I'm going to try to get across to you how unlikely that really is. From your own instincts, without having studied advanced statistics or anything, you knew in your heart of hearts that I was pulling your leg with my little story. But if you have some mathematical sophistication, you can quickly realize the probability of any specific sequence there is absurdly unlikely. There is a law in physics called Borel's law. There are occasions there are often functions in mathematics that become asymptotic to some other value. For example, it gets very close. It never crosses zero, but it gets closer and closer and closer forever. There's a point in mathematics where you have to have a cutoff, where you say that enough's enough, that's sufficient. They call that Borel's law. And any probability with 10 with 50 zeros after it is defined as absurd. Any probability that is more rare than one chance in 10 with 50 zeros after it is defined as absurd. There's a point at which you need to cut off. Okay, so that's called Borel's law. See, I want to sensitize you to something else. When you talk about, we're talking about information here. And one of the most advanced, the frontier of every science today, the frontier is in the field of information sciences. Whether it's biology or physics or anything, the information sciences turn out to be one of the newest but the most cutting-edge sciences. To understand something about information itself, you need to understand there are two extremes that you have to be aware of. You can have something very disordered or very orderly. If it's very disordered, we can call it, if it's sound, we call it noise. If it's orderly, it may just be a signal. It's a word we're listening for or whatever, okay? And music is orderly. If it's disordered, it's cacophony. Now, I'm not going to talk about today's modern music, but you get the idea, okay? There's a term called chaos, which is the ultimate form of chaos, confusion and disorder. It's called chaos in mathematics. Under order, cosmos implies, that's a Greek term, comes from a Greek term, meaning orderly, okay? To bring order out of chaos is what the word cosmos means. That's the root word for cosmetics, to bring order out of chaos. You girls are going to let me get away with that, huh? Okay, let's go. The point I'm trying to get across, on the left we have various forms of randomness. The fancy word for the left side is entropy. Entropy is just the technical term for what you and I think of as randomness. At the right end is when things are orderly, it takes energy and design to make it orderly. There is a basic trend of going from information on the right to entropy on the left. The path of just circumstances, those are opposites, first of all. That's I want you to get across the idea. Information and entropy are opposites. Entropy is total absence of information, okay? If you're an engineer trying to design a communication system, your warfare, you're trying to improve the signal-to-noise ratio. You want to get as much signal and as little noise as possible. And that's also true no matter what you're doing. You're trying to get orderly in here. The path intrinsically is always to the left. You spend a Saturday morning cleaning up the garage. How long does it stay that way? A month later, where is it? The hall closet, your locker in school. You spend energy getting it all straightened out, but as time just goes on, it turns to entropy. That's true everywhere in the world, except one place, and I'll come to that. So the information sciences, there are this whole concept of randomness. I'm using that term because it's more familiar rather than the word entropy. One thing that most of us that have had any math in school may not realize it, but we've been taught in what's called deterministic processes. 2 plus 2 is 4, always. 2 is 2, and I'd say 2 plus 3 is 5. I mean, that's deterministic. And there is another field of mathematics that deals with what they call stochastic processes. These are processes that include a random variable. The height of a person. If you're talking about something stranger, you don't know how tall he is. He's likely to be more than 4 feet and less than 7, but he's somewhere in there, right? That's a stochastic variable. So if you can use that in the equation and know that's within certain bounds, it may have certain distributions, you're dealing with numbers that are not deterministic, they're stochastic. Okay. That leads to a discussion called pseudo-random numbers. It may shock you to discover that it's almost impossible to obtain a random number. If you're a scientist that you need a random number for some reason, you've got a challenge before yourself. Back when I was in the RAND environment, In 1955, the granddaddy think tank of them all, the Rand Corporation in Santa Monica, they published a book called 1 Million Random Digits with 100,000 Normal Deviates. Now, the average layman would look at that and laugh. You know, you open that book, that's literally, I was going to bring one, but it's bulky. You open it up, and it's just lists and lists and lists of random numbers. And if you're a naive, untaught civilian, you look at that and you laugh because you think that's ridiculous. Someone paid good money for a bunch of random numbers. No. It turns out it took the most advanced computer arts of that day to generate this product to have some assurance that they really were random. What do I mean by that? The Rand Corporation had access to the most powerful computers of that day, and they made sure that these numbers had no symmetry, had no predictability, had no patterning, that they washed them to make sure they were truly random. No evidence of design anywhere. And in its day, it was a useful tool for certain kinds of scientists and certain kinds of laboratories that needed a supply of random numbers. Turns out if you need random numbers, you got a problem, because almost any procedure you use to get one isn't really random. It may look like a random. That's why a proper term is it's a pseudo-random number. But to have a source of random numbers turns out in certain fields of study to be essential for certain experimental situations. And so this book was a tool, a serious tool for serious scientists at that time. And even today in a computer, one of the most complicated things it does is to provide you with a random number. It also will be technically a pseudo-random number because it will be a result of some process, which means it isn't really random. And there's tests for randomness, but the tests really mean there's no predictability. There's no patterning. They're not symmetric. It's not, not an even number of odds and evens, except in some large sample and so forth. And so that's not as trivial as it sounds. I'm going through this to get across to you how the defining characteristic of a collection of random numbers is what? The total absence of design. I want to get that across to you because we live in a culture that astonishingly attributes design to randomness. Design in nature is treated as random. We were all the result of a cosmic accident. It's astonishing to realize we live in a culture, in our science and in our psychology, in our schools, whatever, that has ruled out the concept of design as being a source of anything. It attributes that to randomness. That's what the theory of evolution is, an attempt to ascribe. Here we are, we encounter ourselves as the most elegant designs on the planet Earth, and we attribute those designs to nothingness, to absence, to randomness. I want you to understand the absurdity of that and the difficulty of thinking intellectuals that are career-bound in an environment in which if they speak of intelligent design in nature and so forth, they jeopardize their careers. You need to understand that. And we had a speaker here, Stephen Meyer from the Discovery Institute, who's one of the pleasant, refreshing exceptions. And there are people like Philip Johnson, William Dembski, and Michael Behe. These guys are not necessarily Christians, don't misunderstand me, but they are champions of the idea that to acknowledge intelligence as lying behind design. When you find design, it's a fingerprint of somebody's intelligence. And that's the big deal. So, but it's interesting that the Scripture talks about chance in a very strange way. It says the lot is cast in the lap, but the whole disposing thereof is of the Lord. Okay? See, Albert Einstein was famous for saying, God does not play dice. Do you know why? If he did, he'd win. Right? Okay? But I want to talk about, we've talked here about my little simple design. You know, I had these 347 beads, black and white in a row, and they had an unlikelihood of being specifically by design, by randomness. Let's skip a whole bunch of other examples and go to the most elegant example I can find, and that's our DNA, the code of life itself. There are 3 billion rungs on the famous double helix of our DNA. And the code that's involved is a digital error-correcting code. Now, there's not probably one engineer in a dozen that can design an error-detecting code properly. There's certainly a lot fewer than them that can design a code that automatically corrects its own errors. There are such codes, by the way. Most of us are familiar with the 7 or 8 bits that we make to a typewriter stroke called the ASCII codes. If you're, instead of 8 codes, if you're willing to add 3 bits to that, make it 11, you can make it an error-correcting code. There's a computer, NFSQ27, that was built around that technology. You'd take someone on a tour, and while it's running, you could pull a card out while it's running, and it would go on unheeded because it would correct its own errors to a certain limit. And anyway, we have that kind of code designed in our DNA. It's one of the most advanced language designs possible. And it's the same design that occurs in all life. That implies whoever created us created the plants and the flowers and the animals and whatever, because they all use the same code. Wow. There are simplex alphabets, there are error detecting codes, there are error correcting codes. There's adaptive coding scheme. That's where the codes then will modify themselves depending on the context. And we have all of that going on here. We have the DNA, which is the master blueprint. You have a factory inside you. In fact, in every one of your cells, that factory has a master blueprint file place. And when it needs a copy of this, it transcribes a copy of what it needs and then translates that into proteins. The proteins make up the machines. The machines are the machines that handle all this stuff. Now, there's an interesting question that rises here. Which came first? The proteins need those machines to be made, proteins, and yet it takes the proteins to make the machines. 100,000 different kinds, by the way. Which came first, the proteins or the machines? It's the old chicken and egg situation. You can't have one without the other. They both have to be simultaneously designed, by the way. And we could go on and on about this sort of thing. Amino acids. There are hundreds of different kinds that are known, but only 20 are used by living systems. And they're used to construct the proteins that make us up. It's interesting, when you put one of these molecules together, you can put it together 2 ways. You can build a molecule and you can make its mirror image. It turns out that all living things are left-handed. Right-handed equivalents are poisonous to the left-handed ones. All life uses left-handed chirality. The chirality is always left-handed. Now, there's an insight here that we can easily, if this all happened by chance, if somehow cosmic forces cause these things to happen, you'd get half and half, wouldn't you? Half right-handed, left-handed. No, only the left-handed lead to life. So it tells you it can't be random. It had to be selective, you see. But we'll move on here. Now, most proteins in your body are a link of not 347 like this is, but are up to 500 acids long. Some of them are soluble in water. Some are not soluble in water. They're designed that way. And these amino acids can be combined to make 20 different, some of these are nonpolar, some are polar, some are basic, some are acidic. They have certain, they have these chemical aspects to them. And so they have a common structure that allows them to link into a chain, but each one has its own defining characteristics for what it's designed to be. And we have, of these nucleic acids, we've got 4. And rather than mispronounce all the names, I'll just call them A, T, G, C. And when they're copied in the working version for the factory floor, they're copied in a way, and I've color-coded this just to represent those. It's simpler to read. They're designed in such a way that the A's and the T's always link, the G's and the C's always link, and because they have an affinity for each other that way, it turns out the code turns out to be intrinsically self-replicating. It's as if the original is its own carbon paper, if you will. And so when called upon, they will split, replicate themselves, make a copy of themselves, and these complementary pairs, it's intrinsically self-replicating. So we not only have a complex coding system here, it's one that intrinsically multiplies itself when necessary. Now, and there's a sentence structure applied to this. I won't get into all that here for this discussion. But something else goes on that you need to be aware of. Your DNA has certain, they have a sequence of these codes. You make a copy of them for the RNS for the factory floor to start using these things. Machinery comes by and takes certain portions of that out, and the introns are taken out, the exons, as they call it, are then connected. In other words, these things are edited by the chemical machinery to fit the needs. I want you to remember this because we see the same thing going on in the biblical text. It's called an equidistant letter sequence. And I'll show you some of those in the second session. But this is the messenger RNA, as they call it. It's now ready for replication. And so you have the DNA has been copied, slight change in one of the elements in terms of the alphabet, but that's just the way it operated here. And with these three letters, you can define any one of the nucleotides. Now, the genetic code is simply the alignment of those three-letter abbreviations for each of the different things. There's even punctuation defined in the code, start and stop bits and so forth. Now, the messenger RNA then is met by a protein machine that will transfer that, and as it goes along, it reads like a recording head. It starts and it goes along and copies the codes which generate the elements of the protein chain that it needs. This is all a machine that not only operates, corrects its errors, it also reproduces itself. And we could go on, we could spend the whole evening on this, of course, but those that are negatively charged, they associate with positively charged. Those that are non-soluble in water stack. The hydrophobic ones stack in the center. The ones that like the water are on the outside when they're in contact with water and so forth. And the final stable, the thing that then takes a three-dimensional shape that's appropriate for the tool that is designed to be. And that's all designed by the specific codes. And so, now let's just take one example, and I'm going to pick hemoglobin. Hemoglobin is obviously an element of your blood. It happens to take 574 amino acids in length to make one. And these are the numbers. You have 36 of those and 60. I won't mispronounce all these to go through, but there's 574 in total, okay? Now the question is, they have to be in a specific order. If they're not in a specific order, it's called hemoglobinopathy. It can be deadly. And so this is called specificity, and there's a formula for producing this. It turns out that if you have a code not of 2 but of 20, and you got 574 pieces you need in a row, that'll turn out to the number of possible arrangements you could have is 10 with 650 zeros after it. Are you going to leave that to chance? Heavens no. If you got the wrong one, you got death on your hands. And so only one of them is hemoglobin. And if you change just one of them, you have hemoglobinopathy, or death, if you will. Now, chance itself is pretty inefficient. Say this just happened by evolution, just randomness. Well, the probability of random chance of 347 beads are black and white, we said was 10 with 104 zeros after it, right? A hemoglobin molecule, 574 elements from an alphabet, not of 2, of 20. There's 10 to the 650th power permutations possible. Only one of them is hemoglobin. And if you miss it, you die. Heavy stuff. Remember Borel's law? Anything with more than 50 zeros is defined as absurd. Hemoglobin to happen randomly is more than, is really, really, really absurd. Just as is my little example with these silly little beads, okay? To give you some feeling for these numbers, there have been only about 10 to the 18th seconds in the history of the universe, if you accept a 13, 14, 15 billion year lifetime. How many atoms are in our galaxy? Only 10 to the 66th. These are giant numbers. There are only 10 to the 80th particles in our entire galaxy, subatomic particles. And of course, probably more than 10 to the 50th defined is absurd. The specificity of a hemoglobin molecule is way, way beyond the possibility of it happening by chance. It had to be deliberately designed, is the point. And so, what's the chances of doing this by chance? That's equivalent to winning the lottery, not just once, but every day without missing for 90 days. That's, I think, another way of recognizing what's absurd. There's a basic equation that people would have you believe, if you go to a biology class, that matter plus energy plus randomness, entropy, can equal life. That's what you're taught, and that's what kids are taught in school. Take the entropy out. The correct equation is matter plus energy plus information equals life. I usually do a thing with a peanut butter jar or something, open a brand new one and so forth. And when I open up, I act surprised there's no new life inside. Aren't you glad? Do you realize that the food industry conducts billions of experiments every day, every year, dependent on the fact that that first equation is not true? Matter plus energy plus randomness does not generate new life, or you would have contaminated food. A spore or something else has to get in there to have it. If it was just randomness, the food industry would be impossible. No, they bank on the fact that matter, if you seal it properly, wrong information won't get in there to give you. You don't want, you open a jar of baby food, you don't want new life in there. You've got another life you're trying to take care of. Okay. Well, let's talk about, there's a lot of talk in certain quarters about trying to search for extraterrestrial life. Somehow, a lot of people are just somehow focused on the idea that there must be life in the universe somewhere, and they're trying to find it. And they call that the search for extraterrestrial life or extra intelligence. The whole process of looking for external life often leans on the Drake formula, or sometimes called the Green Bank formula. And basically, N is the number of civilizations in the galaxy capable of interstellar communication. That's what they're trying. 84 scientists in 1971 gathered at the USSR Academy of Science to try to pool they came from all the different fields of knowledge, to try to pool their estimate. What's the likelihood of a civilization in our galaxy capable of extraterrestrial communication? Well, that's N. They would get an estimate of N here. R was the average rate at which stars develop during the lifetime of the galaxy. That's an estimate that astronomers were willing to come to some agreement on. From that group, what fraction of stars have planets? Well, we found very few of them do, but they make an estimate of whatever that is. How many of those planets per star are capable of supporting life? That's the next element. What fraction of those planets actually have life? What fraction of planets have intelligent life? And what fraction of the planets with intelligent life capable of interstellar communications? Each one of these is a fraction. It's a product of the whole shebang here. And L is the average lifetime of society capable of interstellar communication. It was very interesting to read the papers of these 84 scientists and the proceedings of that conference as they wrestled with all this. And they tried very hard to be optimistic, but reluctantly had to admit to themselves that by the time you go through this, that average rate stars develop, what fraction of these have planets, relatively few. How many of those planets, what per star, are capable of supporting life? That turns out to be very, very rare. I'll come back to that in a minute. What fraction of those actually have life? How much of that life would be intelligent? How much would that be so intelligent? As you go through all of this, you quickly discover that what you're really dealing with here is a miracle. And so, even in scientific, empirical terms, it is highly unlikely that you'll have anyone else out there. Because there's another thing that they inadvertently were estimating. And that's something that is called within the secular scientific community the anthropic principle. Strange term. Paul Davies, the famous scientific writer, said it seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. That's his conclusion. And what does he mean by that? Well, what they've discovered, as they try to make a mathematical model of everything we know about the universe, we discover that there's some parameters that turn out to have to be exactly where they are, or it doesn't work. It's the appearance that is given that the whole universe seems to have been designed specifically for man. Now, those who have read the Bible say, no kidding, Dick Tracy. But the point is, this is a great insight. If you got a PhD from one of these, from MIT or wherever, that's a remarkable insight for you. Anyway, so in constructing the mathematical model, what they think they know about the universe, there are hundreds of delicate ratios, if altered the slightest, would render life impossible. Some as little as 1 part in 10 to the 55th, by the way. That's a very itty-bitty adjustment. I'll come to some of these in a minute. The first thing you need to refresh your memory from your high school science is there are 4 forces that are operative in the universe. One's called gravity, one's electromagnetic force. Then there are 2 nuclear forces. One they call the strong nuclear force, another force, the weak nuclear force. These 4 forces are the only forces that have been observed in nature, and they're well observed and well understood in many respects. Gravity. What is gravity? Well, that's what causes an apple to fall to the ground. That keeps our feet on the floor. That binds together our solar system. It keeps the planets in their orbits. It keeps the Earth and the planets in their orbits. It prevents the stars from exploding. It says here, but you'll discover that ain't true either, but I'm going to come to that in a rather rebellious paper at the end of our series. Guys, the galaxies and their motions, these last 2 are the common beliefs of astronomers. And there's now some scientists that are debunking that myth, by the way. But coming back to this. The electromagnetic force is what holds the atom together. It determines the structure of the orbits of the electrons in the molecule. It governs, thus, the laws of chemistry. It also the forms of this include X-rays, radio waves, and light. Those are all electromagnetic phenomena. It can overcome gravity on the Earth. I want you to realize that electromagnetic force is more powerful than gravity. In some cases, by 10 with 39 zeros after it. Electromagnetic force is vastly more powerful than most astronomers have any serious apprehension of. And anyway, it can dominate other forces down to the size of the nucleus of an atom. It's dominant down to the nucleus. From there, the weak and strong forces seem to take charge within the atom. But that's the electromagnetic force. And there are 2 nuclear forces. The strong nuclear force, what binds the protons and the neutrons in the nucleus of the atom. And positive and negative things tend to repel, but the strong nuclear force is what binds the nucleus together. The balance between the strong force and the electromagnetic force limit the nucleus to about 100 protons. That's why your periodic table is that big. It isn't bigger. Okay? That's because of the ratio between those 2. And the energy release substantially greater than the electromagnetic chemical force. In other words, you can gain some energy from electromagnetic things by normal chemistry. But the strong nuclear force is what you're dealing with when you've got a nuclear situation. And that's also how the stars shine, which is essential for life. The weak nuclear force, it governs the atomic instability and radioactivity. It controls the disintegration of the heavier nuclei. It can create heat, such as the decay of the radioactive elements in the Earth's core and in a nuclear power plant, and so forth. Well, there's gravitational coupling. This is a ratio that we experience. All stars more massive than our sun by 1.4 times. If they burn too rapidly and too inconstantly to maintain life-supporting conditions on surrounding planets. That's if the coupling was stronger. If this coupling was weaker, all stars would have less than 0.8 times the mass of the sun. There would be no such thing as heavy elements. You just have hydrogen and helium, that's all. So it turns out that ratio has to be a certain ratio or the universe doesn't exist as we know it. Electromagnetic coupling. If it was weaker, molecules for life would cease to exist. If it was stronger, molecules for life would cease to exist. In other words, it's exactly the strength to give us the spread of elements that make up the periodic table. The strong force coupling. If it was slightly weaker, multi-proton nuclei would not hold together. Hydrogen would be the only element in the universe. If it was slightly stronger, nuclear particles would tend to bond together more frequently, more firmly. Hydrogen would be rarer in the universe, and the supply of various life-essential elements heavier than iron would be insufficient. So it's just where it should be, so to speak. The weak force coupling. If it was larger, there'd be no helium and no heavy elements. If it was weaker, it would all be helium and overabundance of heavy elements. See, these things happen to be just the right relationships. The ratio of electron to proton mass. If it was larger, molecules would not form and life would be impossible. If it was smaller, molecules would not form and life would be impossible. It's exactly the ratio that makes life possible. The distance from the sun. If we were closer to the sun, we'd be too warm to maintain a stable water cycle. If we were further from the sun, it would be too cold to have a water cycle. Okay? Surface gravity. If the gravity was stronger, our atmosphere would have too much ammonia and methane in it. If the surface gravity was weaker, the atmosphere would lose too much water. It happens to be just the right balance to give us the atmosphere we need. The thickness of the Earth's crust has been studied. If it was thicker, too much oxygen would be transferred from the atmosphere to the crust. If it was thinner, volcanic and tectonic activity would be too great. So even the thickness of the crust. The Earth's rotational period. If it took longer to make a day, the diurnal temperature differences would be too great on the planet Earth. If the days were shorter, atmospheric wind velocities would be too great. All this has been analyzed. They discover as they play with these things that they're where they need to be. The actual tilt of the Earth. If it was greater, the surface temperature would be too great. If it was less, the surface temperature would be too great. Okay? The albedo, that's the reflectivity of the Earth. If it was greater, a runaway ice age would develop. If it was less, a runaway greenhouse effect would develop. It's exactly the reflectivity to prevent those two extremes. The Earth's magnetic field. If it was stronger, electromagnetic storms would be too severe. If it was weaker, inadequate protection from hard stellar irradiation would be inadequate. This one I love, the ozone level. Boy, haven't we heard about the ozone level? Well, if the ozone level was greater, the surface temperature would be too low. If the ozone level was less, the surface temperature would be too high, and there'd be too much UV radiation at the surface. And as we're reminded by the ecologists again and again, 0.1% change will bring cosmic doom, right? Well, if that's the case, flip that coin over. Who made it exactly that number already? And more importantly, who maintains it? You see, they inadvertently, in their screaming that the ozone level might change and that cause cosmic doom, they're acknowledging that it happens to be exactly where it needs to be to support life. See, that coin has two sides. CO2 and water vapor levels. If they were greater, a runaway greenhouse effect would develop. And if it was less, the greenhouse effect would be insufficient. It's just where it needs to be. How amazing. That requires a balance, not just between animal life and trees, but both together. So there's a whole cycle here that has to stay in balance. So we've gone through a whole list of these, and some of these may surprise you. There's actually more. I've just selected some that I figured we could, just in a quick pass-through, relate to a little bit. So it turns out that at the atomic and subatomic level, the slightest variation in any one of the primary constants of physics, if it was different, some are as sensitive as 1 part in over a billion would cause life to be impossible. Okay? The more rare these relationships are, the more they unequivocally reveal both skillful design in their origin as well as diligence in their maintenance. They weren't just set up and left alone thousands of years ago and left to turn to pot. No, they're maintained. It's what Paul tells us in Colossians, that by all these things, by Jesus Christ, they are held together. By whom? By Him. Wow. You know, we've invented the most insulting God of all. You know, the ancient pagan cultures would carve out things out of stone or wood, and then they'd carve it, and then they'd bow down and worship, and they'd ascribe the creation to their so-called gods. In our culture, we've invented the most insulting God of all. More insulting than idols of bronze or wood or silver or whatever. Randomness. Nothingness. It all just happened by itself. That's more insulting to the God of the universe than attributing it to some other God. We're saying one wasn't necessary. Wow. Randomness, total absence of design is what they're saying. Ridiculous. I want to give you an example where the anthropic principle actually led to a scientific discovery. Fred Hoyle, so he was benighted in 1954. He predicted and then discovered the previously unknown energy levels in the carbon-12 atom. How? From his sensitivity to the prevalent patterns of numerical design in the universe. Fred Hoyle, there was resonance involving the helium-4, beryllium-8, and the carbon-12. The mass energy of each nucleus was fixed and cannot change. The kinetic energy depends upon the internal star temperature, which can be calculated. Hoyle predicted that there must be a previously undetected energy level in the carbon-12 nucleus that would resonate with the combined energies of its constituent parts under the conditions prevailing inside stars. Subsequent experiments confirmed this prediction precisely. For most of us, not a big deal, except what's interesting was his methodology. He predicted it on the basis of his confidence of design in the universe. And Hoyle applied the anthropic principle to predict in advance, not by hindsight, the energy level at 7.6 million electron volts. Anyway, so the anthropic principle, this is well-traveled ground for most of you that have done any reading in cosmology. But let me tell you, there's a surprise that's a relatively recent discovery. Not only was the universe designed for man, we now realize, there's evidence, that it was designed to be discovered. And we're indebted to a couple of interesting guys who published a book about this, that the planet Earth is uniquely positioned for life, and it's uniquely positioned to discover life. Its position in the galaxy is such, if it was anywhere else, we wouldn't be able to see what we can see where we are. We're not too close or too far from the center. Much of this comes out of total eclipses. And I was going to make a diagram, but I had too much stuff here to cover, so I didn't want to take the time. But if you make a diagram of a total eclipse, you've got the Earth, you've got the moon in the way, and the sun, and the distances and sizes are precisely such that the moon appears to completely obliterate the sun exactly. Not too small or too big. If it was a little smaller, you would just see the sun eclipse it. Or make it blot it out. If it was a little larger, you would totally, it's exactly the size of the sun. And what that causes you to be able to see that you normally can't see is the corona. There are electromagnetic effects that are gigantic surrounding the sun that you can see only during a total eclipse. And it's because of the total eclipses that we discovered spectroscopy, and out of spectroscopy we have the tool to tell what stars are made out of, how much they weigh, how old they are, things of that nature. And so the point is the precision of size of the sun, the moon, and their positions is exactly where it would have to be for us to discover spectroscopy. Any other way, we never would have discovered it. Now, we're also positioned within the visible spectrum. It turns out that if you change that a little bit, it really messes up your signal and noise. But anyway, All of this implies teleology. In other words, it was designed for that purpose. It's a purposeful design. It's not only designed, it's a purposeful design. There is both a book and a DVD that you need to get if you're interested in this, called The Privileged Planet. Came out in 2004 by Gonzalez and J.W. Richards. Gonzalez and Richards have made, the book is terrific. The DVD is the most impeccable thing I've ever seen. I encourage you to track it down. And the Privileged Planet. It's really worth your look through. Well, in thermodynamics, we have three laws. The conservation of matter and energy, most of you are familiar with that, the so-called first law. You can't make or break energy or matter, and that there's no way to win is what it says. The second law is the entropy law, the bondage of decay, Paul calls it in the book of Romans. Not only can you not win, you can't break even. In other words, there's always going to be a loss. There's no such thing as a 100% efficient machine. There's always a loss of efficiency. And that goes to entropy. There's a third law. Everything has positive entropy, which simply means you can't get out of the game. Most people are not familiar with that. I won't get into it here. I want to focus on entropy, the bondage of decay. We talked about that when we first started a little bit. Entropy in Scripture. You know, the Scripture talks about this. Speaking of the heavens, they shall perish. They can grow old as a garment. Isaiah 51:6, the earth will grow old like a garment. Things age is the point. Heaven and earth will pass away, the Lord reminds us in Matthew 24. There's a connection, we believe, we suspect, I should say, between entropy and the creation itself. There's a number of us that suspect that the entropy laws were introduced at the fall of Adam. I say that because of Romans 8:21, where Paul tells us, because the creation itself will be set free from its bondage to decay and obtain the glorious liberty of the children of God. The day is coming when that's going to be repealed. And that's exciting. But that also tells us something, that bondage to decay is apparently limited. See, everything we know about our creation is post-curse. Everything we know about creation is after Genesis 3. So we can only guess what it might have been before then. So we've talked about randomness. We've talked about, in our previous thing, we talked about infinity in the macrocosm, a finite universe. Last time we took a look at bigness, the largeness, if you will. And as we do that, we get, with man in the middle, as things get bigger, we talk about largeness and how big. The big discovery, of course, is that the universe is finite. It's not infinite. It might be expanding, but it's finite in size, not infinite. Well, the Big Bang leads to the ultimate heat death. We're caught between whatever the singularity that started it, commonly called the Big Bang, and the ultimate burnout, which it will eventually happen. Well, there's a second imputed concept. These are two concepts that are used in mathematics that we can't find in the physical universe. Randomness is one of them we talked about. Infinity is the other. And the macrocosm we talked about last time, when we talked about beyond time and space. In the next time, we're going to talk about the microcosm, smallness in terms of quantum physics. And it's shocking to discover there's a limit to smallness. You can divide things in half, and always take whatever's left and divide it again until you get to a certain point at which, if you try to divide it, it suddenly is everywhere. It loses locality. And there's a Planck length of, in terms of length, it's 10 to the minus 33 centimeters. There's Planck time of 10 to the minus 43 seconds. There's a unit of time you can't get smaller than. And so the point is, we are in a digital simulation. Our entire reality is a digital simulation. Our so-called reality is actually a virtual reality, and we need to come to grips with that. And so that's it. We are in finite limits, digital simulation, and the metacosm. There's in fact, the Scientific American summarized it so beautifully in their article in June of 2005. Our universe is but a shadow of a larger reality. Well, that's what the Bible has been saying all along. And we'll talk more about that as we get into next time. But I mentioned it before, but I'd like to review again something I think it fits this topic so perfectly. And that's certain constants of the universe. It turns out that of all those constants we talked about, there are two constants that are dimensionless. And one of them is pi. We've all dealt with that in school. It's the relationship between the diameter and the circumference of a circle. And it's a strange number. We'll come back to that in a minute. The other one you may not have run into unless you've been in a very advanced math, and that's the thing called E, the base of what they call natural logarithms. And there are two key verses in the Bible about creation. Genesis 1:1, of course, and the equivalent in the New Testament, John 1:1. They both announce the creation. It's interesting if we examine those two verses very, very carefully. First verse, Genesis 1:1, in the beginning God created the heaven and the earth. If we look at that in the Hebrew, remember it goes from right to left, every letter, both Hebrew and Greek, have the peculiar characteristic that every letter has a numerical value. And you can take advantage of that in a number of interesting ways. In this case, if you take the number of letters in Genesis 1:1 and multiply that by the product of the letters, and you do the same thing, you divide it by the number of words and the product of the words. See, every letter and every word has a numerical value. If you go through and apply those and take that quotient, you come up with 3.1416, which happens to be the value of pi more accurately than you probably used in school. You probably, when you were in school, used 22/7. If you're in engineering class, you might have used 3.14159, but it actually goes much longer than that. Here to 4 decimal place accuracy. Now, the average person will say, wow, that's just a coincidence. Maybe. I think it's a very unlikely coincidence, by the way. But let's go on here a little bit. That happens to be pi times 10 to the 17th. There's a guy by the name of John Napier that you probably haven't run into, unless you were in advanced math. He was the discoverer of what we call logarithms. And natural or Napierian logarithms are named after him. That's when the logarithm is to the base of e. It has some very peculiar characteristics when that happens. He also was the guy that promoted the use of decimal point and fractions. He happened to be an activist for the Reformation and Protestant affairs in Scotland, by the way. And it's interesting in those early years how, whether it's Isaac Newton or whoever, these great scientists were also great churchmen, by the way. Or I should say, at least took the Bible seriously. Well, E is a number you may not have run into, but it's very widely used in mathematics. It's defined by an expansion, which I won't go into here. Its limiting value is about 2.718281828, and so on. The number E forms the base of natural or Napierian logarithms. Okay. What makes it so interesting? It appears in exponential function, e to the x. It's the only function having a rate of growth equal to its own size. In the language of calculus, it's the only function having a derivative equal to itself. It's the fundamental function for equations describing growth or many other processes of change. For that reason, you find it in wave mechanics, in electrical theory, in advanced math, distribution of prime numbers, who knows why, defined by E, the limit, and so forth. It's usually approximated by 2.718281828, and so on. Okay. What am I getting at? Let's take the other verse. We saw Genesis 1:1 led to pi. Let's take John 1:1. In the beginning was the Word was with God, the Word was God. If you take that into Greek, again, Greek has a numerical value for each letter. Do exactly what we did with Genesis 1:1. The number of letters times the product of letters, divided by the number of words times the product of the words. You get E to 4 decimal places. That's astonishing. That's astonishing. I'll say, what a coincidence. My rabbinical friends will tell me coincidence is not a kosher word. But this is the kind of pointer or kind of signpost that should wake us up and to realize there is a marriage, if you will, between the real creation and a message from our designer. This is E. And of course, as I say, Scientific American pointed the 3-dimensional constants that are shadows of a larger reality. And that's what the Bible has said all along, in Hebrews 11:3 and 1 Corinthians 15 and a lot of other places. The second verse in Hebrews 1, hath in these days spoken unto us by his Son, whom he hath appointed heir of all things, by whom also he made the worlds. Who made the worlds? Jesus Christ, indeed. By whom he made the worlds. The word worlds there in the Greek is ionis, which really means time domains, in the plural. Some Bibles say ages. It's generally regarded by scholars to mean the entire creation, of course. Jesus is the creator. That's all through the scripture, as you know. Well, for our next session, I'm going to ask you a question. Is there actual evidence that the Bible is actually an extraterrestrial message from the master designer himself? Is there, not a belief, is there evidence of that? Empirical evidence of that? And if there is, how sure can we be? Lord Calvin is famous for saying that until you can measure something, you really know very little about it. Well, can you measure your confidence that the Bible is... How many think the Bible is the Word of God? Got about 90% of the hands to go up. Okay. No, I'm kidding. All right. My next question is why? Why do you believe that? Somebody told you that? You take it in confidence because everybody around you feels that way? No. Well, are you really sure? How sure can you be? You're going to be astonished to discover how sure you can be on an empirical basis for what you believe. And next time, we're going to take Beyond Coincidence Part 2, in which we're going to explore empirical proof that that which is in your lap is provably from outside our time domain. I'm always so tired of these well-meaning commentators on television say, well, you can't prove the Bible but, and they can make some positive statement, but they preface it with, you can't prove the Bible but. They're wrong, you can. We'll show you how next time. We'll also show you how sure you can be that Jesus Christ is who he said he was. So with that, let's stand for a closing word of prayer.